Hello, we'll now come on to our final one on the solar system. That's on exoplanets. So what is an exoplanet? An exoplanet or an extrasolar planet is a planet outside the solar system. So if you remember the last talk we spoke about the origin of the solar system, where we said that planet formation is essentially a byproduct of star formation. That is, when stars are formed, planets get formed along with them, right? And therefore, obviously, the next question we would ask is that how many other stars do have planets, right? So it's expected that a large number of stars do have planets, and that's what we call exoplanets. And one of my favorite arguments is the argument given by Carl Sagan in the book as well as in the movie Contact, supporting exoplanets, where he says that the universe is a pretty big place. If it's just us, seems like an awful waste of space, right? That's what Carl Sagan said. And hence, there was always this urge to look for life outside the Earth. So you look for planets and then probable life on those planets. Uh, what's also very new about this thing is that, exciting about this, is that in 2019, last year, one half of the Nobel Prize was actually awarded for exoplanets by work done by Michel Mayor and Didier Queloz for their discovery of the first exoplanet orbiting a sun-like star. Right? So in 1995, this work was done in 95 by them, where they did this breakthrough of a planet around another sun. And it's a Swiss team from Geneva University, and they discovered a planet 51 Peg, which is about 48 light years from the Earth. Why do we look for exoplanets? Well, actually, it dates back to the days of even Bruno. Bruno is in the 16th century, where he actually spoke about infinite universe and worlds, where he actually proposed the idea of life being there on other worlds, which was considered blasphemy and in those times, and therefore Bruno paid with it for his life. He was burnt alive and for giving such blasphemous ideas. And there have been, since a long time, there have been various teams, various stars which people have been trying to check out, various techniques. And most of these, it was not successful for a very long time. And essentially the question is, why were these techniques not, why were these attempts not successful? So one could be that the techniques were not sensitive enough, or perhaps there were no planets after all. And the first planet, evidence of exoplanet was not in 1917, but not recognized like that as such. And the first confirmation of detection actually occurred before the work of Michel Mayor, which was in 1992, which was of a detection around a pulsar. Now, what are the standard methods which we use to actually look for exoplanets? So one of them, which you see on the top of here, is the radial velocity method. So let's consider, for example, you have a host star and you have an exoplanet going around the host star. Well, in that case, if you have this kind of an orbital motion, then there are going to be times when the star is coming towards you. And for example, in this case, the planet is going away from you. And hence, if you actually measure the radial velocity, which is done through spectroscopy, you can actually look for the spectral shift, the delta lambda by lambda, and use that to find out the velocity of the object and actually determine the orbital motion of such a system. This is also used for binary stars, for example. You can actually use this kind of a method. The other method is that of transit photometry, that for example, you have a star and you have a planet coming in front of the star. So obviously, if the star had a certain brightness versus time, which is some constant value, then when the planet comes in front of it, there's obviously a dip in the brightness. And as the planet moves off, you again have a rise in the brightness. So that's what's called transit photometry, or the transit method. There's also the microlensing method, that you could actually have it behaving like a lens. You already know about what is called gravitational lensing, and you can have this planet behaving like a lens, which would actually cause microlensing. And then the ideal way would be actually to do direct imaging, to actually manage to image a star as well as the planets going around the star. So these are the essential four methods of detection of exoplanets. So like I spoke about radial velocity, let's say I have this massive star and the planet. There's a center of mass over here. So the star goes around this, both of them go around their center of mass. And the planet is obviously very faint. It's not very bright. And therefore, what you would actually see is you basically see a wobble in the star's position or its velocity, right? Because you're not going to be able to detect the planet. The planet is not going to be bright enough, not easy to detect. And therefore, the wobble would actually give you an idea of the period of this revolution, and hence you can actually get it. So the radial velocity method is basically based on, like I mentioned, the method of Doppler shift. That means you have a Doppler shift from the light coming from the star and the planet. One would be blue shifted, one would be red shifted, and that's how you could actually do it. So the Geneva team, which we spoke about, they actually use this kind of a method. And essentially, if supposing one was actually observing our solar system, right? So obviously, even the Jupiter causes a wobble to the sun, which is approximately a 13 meter per second kind of a wobble, while Earth forms a very small wobble. And but the HARPS instrument, which we have on the ESO 3.6 meter, this actually has a measurement of 1 meter per second. Okay, that basically gets determined by the resolution of your spectroscope, your delta lambda by lambda, and that would basically determine what is the kind of velocity measurements you can do. And with the HARPS instrument, you can get this kind of a precision. So if you had an Earth-like planet, you will not get it, but if you had a Jupiter-like one, you would be able to do it. So essentially, you would actually have a radial velocity variation, and you can actually use that to find that. So it's obviously a big feat, even in instrumentation, to get the kind of precision we are talking about, right? So here I have another animation to show you. Here you have the star, you have the planet, and like you can see, as it's going, you have the spectral lines are getting shifted. This is the red side, and so this planet has gone away, so it's gone red side, and now it's going red and blue, and hence you can see a variation in the spectral lines. Now, another problem if you're actually doing it is you cannot exactly measure the exact mass for a planet without knowing the tilt of its object, right? So the Doppler shift basically tells you the velocity, but it is in terms of a projection, right? You are not seeing, you don't know what is the angle at which you're getting it. And therefore, Doppler data basically gives you lower limits on masses. You do not know the actual, there's a range because we don't know the tilt of the orbit, right, of the system we are observing. And like I mentioned earlier, this was a years of effort. So for example, Jupiter would cause the sun to wobble by 10 meters per second. And actually the problem was actually of achieving Doppler velocity measurement precisions, right? You need a measurement precision better than 1,000 meters, 300 meters. So there are a whole bunch of people, I'm not going into the details, but there are a whole bunch of people who actually went into detailed instrumentation work to actually improve the precision with which this velocity is actually measured, right? So like I mentioned, this velocity, this is the radial velocity, basically is the delta lambda by lambda, which is the resolution of the spectroscope which you're using. And so if you want to, if in our solar system, if you were actually the gravitational tug of Jupiter at 5 AU distance, causes the sun to move at a speed of 12 meters per second. In terms of wavelength, if you were to do it in wavelength, this would be a wavelength shift of 10 power minus 14 meters, right, in visible light. So if you were to put this with delta lambda by lambda, you would have this kind of a wavelength shift. And that is the kind of thing which we are trying to measure, which makes it such a difficult job to actually make such a measurement. Now, a strange orbiting, what they found in their team is that there was a strange object orbiting 51 Peg, which was twice the size of Jupiter, but 7 times closer to its star than Mercury is to our sun. And initially, they were a little worried about their readings, their observations that they had, because this was the kind of object that they seemed to get. And the object actually made no sense with our general models of planet formation, basically because this object was a Jupiter-like planet, but it was very close to its sun, right? So you can see it's twice the size of Jupiter, but 7 times closer to its sun than Mercury is to our sun, right? So obviously they were very confused about this kind of result which they got about their planet. One of the possible solutions was migration. That we know that in our solar system also there has been planetary migration, in the sense the planets are not exactly at the same positions where they were formed. They have migrated from their original positions. So one possible reason could be that was it a migration, and hence the planet came closer to that. And so most probably that's what actually happened, that this Jupiter-like planet actually formed further away from 51 Peg and then migrated towards the star for some reason or the other. The reason we are not too sure, but it seems to have migrated. So like I mentioned, planetary migration. So you often have a young planet's motion. It actually causes waves in a planet formation disk, and that could cause tug, and that could cause the planet to move from its original position where it was formed. The next method, let's come on to it, is planetary transit. Like I mentioned earlier, you have a planet coming in front of the star, due to which there's a dip in the brightness, right? Now the problem is this: in this picture which I've shown you a very nice dip, a very clear dip. So you can see it's half the brightness is gone. But you see that does not correspond to this image at all. Because what is going to be the difference in the dip? The depth that you're going to have is going to be a ratio of the areas, right? So ratio of the area of the star to the area of the planet. So it is Rp squared, if Rp is the radius of the planet, divided by R sun squared, right? And that will actually give you the dip. So for example, if you take the sun and the earth, right? So if I take R squared of the sun, the radius of the sun 7.1 into 10 power 5, and then I take the earth 6.4 10 power 3 squared, you'd basically see that here I get a 10 power 5, 10 power this thing, so 10 power 4, right? So this is, the ratio would be 10 power 4. Yeah, that means the brightness would decrease by 1/10,000th of the normal brightness, right? And that is the kind of depth you are going to look for. So one of the Kepler is another satellite that has been checked to actually send to actually look for light curves of planets, of stars, and it's basically used to look for exoplanets. So basically Kepler works on what is called this transit method, where you're basically trying to measure how much is the dip which is caused by this thing. So typically brightness, this is just to give you an idea of what is the kind of things we are talking about. So for example, if the planet in this case is a hot Jupiter, you can see that here you have a 1% dip. So if this is 1, this is coming in the third decimal, this is 0.994. This is the kind of dip which you need to determine, even if you have a Jupiter-like planet, right? So this is a Kepler-like curve of an exoplanet called HAT P7b. And in this case, you can see that this dip is so minuscule, right? So if you have to actually look for a dip, it actually makes such a this thing. The other complications in transit methods is that it is considered that you need to have typically at least 3 transits to confirm the size of the planet. There could also be a problem depending upon number of planets. It needn't be a single planet going around a star, it could be a number of planets. The orbital period, the inclination, all these are the things which actually make the transit method slightly difficult, right? It's not slightly difficult, but very difficult, because this is the kind of precision you are trying to look for, right? So over here, there's another exoplanet which I'm showing over here. And you can see that here you had an exoplanet for which the transit period was 1.6 hours and the depth was in magnitude scales. Sir spoke to you yesterday about magnitude scales. It's 0.03 magnitudes. Now 0.03 magnitudes is something very, very difficult to measure, especially if you're doing it from a ground-based telescope. Then even, by atmospheric variations, you could have such a variation in magnitudes. So you would never know whether this difference is coming because of the sky, is there a change in the sky, or is it happening because you actually have a dimming of the star, right? So making measurements of this kind is also very distinct, but this one has been done with a 16-inch telescope in 2016, where you can see it's very beautifully got for this thing, right? The other method we have is what is called the microlensing method. That is, for example, you can see the animation over here. So if the lens star is orbited by a planet, the planet will further deflect the light from the source star. And we can detect the planet, you're going to detect it indirectly by measuring the magnification curve and observing the small bump it produces. And if the deflection is strong enough, the distant star appears to be 2 stars. So you can actually get 2 stars. And therefore this microlensing effect, which is caused by the presence of this planet over here, it can be measured. in rare cases and very difficult, but it can be done. So here I have another thing where you have this happening, and you can have a lens effect happening like this, where you get such an effect coming here, right? Another animation here we have of the lensing effect, that you have this planet going around here, and because of that, when you're actually looking at it, the star gets slightly magnified. It behaves like an optical lens. Gravity also behaves like a lens, exactly the way optical lenses behave, and hence you can have an enhancement of the brightness of the star, which is the slight rise, which is a typical microlensing signature, right? But again, this brightness is a small amount, and hence it has to be very precisely measured. The last method we spoke about is the direct imaging of the planet. That is, for example, you have a star and you try to directly image it. Obviously, it's very difficult because of the extreme contrast, right? So for example, if you were looking at Jupiter and the Sun at a 5 parsec distance, then you would actually, it would be a 1/10⁹ kind of variation. So it would be varying by a billionth time would be the brightness of Jupiter compared to the Sun. So imagine you have this object which has a brightness, and you have Jupiter with 10⁻⁹ times as bright as that. What is the probability that you would actually manage to observe it? The other problem is that if the planet belongs to the star, it will have a very small angular separation, and hence you may not even be able to discern this thing, right? But there are various telescopes and efforts being made to actually sit and image that. So how would you do it? A standard method used is by actually putting what is called a coronagraph. You cover the light of the star, and you actually, this is actually done for the sun. This is the SOHO spacecraft, which actually does it for the sun, covers the sun and observes the corona of the sun. Or for example, in eclipses, what actually happens is the sun disk gets covered and we can actually see the corona, right? So in this case, you can actually use a coronagraph and actually try to do it. And they also use methods like what are called adaptive optics, where it is also used. There are other methods used. Here you can see this, the VLT, Very Large Telescope infrared image of a hot young planet around a brown dwarf star. You have images over here. So there are a few examples even of direct imaging where we've actually imaged planets going around stars. So here you have the formula system, and you can actually see the imaging done for that. And there's another system over here, HR8799. You can see the scale over here. This is 20 AU, and that's the kind of distance at which we are measuring these things. Beta Pictoris, I spoke to you this about in the last lecture also, where you have Beta Pictoris and you have the planet going around it, again being imaged by the VLT. Now the Kepler mission, which I spoke to you a little bit about, was a mission which was actually designed to basically look for extrasolar planets. Like I said, the precision we need in magnitudes is very, very precise, and therefore best it is to actually take such observation from outside the atmosphere. So Kepler was basically a 1.4 meter telescope launched in 2009 to actually observe the same part of the sky. Okay, the size about of the fist at arm's length. So Kepler looked at the same part of the sky and actually plotted light curves for all the stars in that region. Okay, so Kepler data is available online. You can always use that to analyze it and actually look for planets. And after a certain stage, the Kepler mission, there were some problems in the spacecraft in 2013, and therefore a compromised configuration was got for Kepler, which is called the K2. And with the K2 mission also, which is Kepler itself, but with certain lesser capabilities, you still had observations coming from Kepler using the K2. NASA launched another satellite called TESS, which was launched in 2018, again to look for exoplanets, like the way Kepler has. Again, TESS data is also available online, and a lot of students can work on student projects using Kepler data as well as TESS data to actually look for exoplanets. So here I have an example of an astronomy student in Canada who discovered 17 exoplanets using Kepler data, and such things are very much possible. And you have a lot of, also exoplanets can be looked through radio emission. I won't talk about that too much, but it's just good to know that it's possible. So there have been various exoplanet missions. Like I showed you, Hubble itself was giving you some amount of imaging. Spitzer is in infrared, Kepler we spoke about, TESS, and the new one which is going to go, which is called the JWST, the James Webb Space Telescope. All these are missions which actually plan to look for exoplanets in the future. Now, what do we know about exoplanets? If we actually try to look at their properties, you can see that their properties are such that you have certain hot Jupiters. The orbital periods also range from 1 to 1,000 days for rocky planets and various kinds of this thing. And here I have a plotting of the different methods used to actually detect them, right? Sizes of planet candidates, if you look at them, they range Earth size, this thing. There's obviously an observational bias by to which we look, we find the bigger ones. And if you actually plot a mass radius relationship, this is important because actually it gives an idea of the density of the problem, right? Mass by radius actually gives you a density estimation, so you can actually use it to look for density estimates of planets. What else do we know about them? We actually can plot the orbital eccentricity versus the average orbital distance over here. Here we've also plotted our solar system planets so that you can see where do they lie on this. How do they compare to the extrasolar population? If you see their orbits, most of the detected planets have orbits similar to that of Jupiter's, and planets at greater distances are harder to detect, obviously, using the Doppler technique. If you actually see the orbital properties also, orbits of some extrasolar planets are more elongated than those in other things. So you have a whole variety. What about the multiplicities? Some stars have more than one detected planet, so you actually look for multiplicities. You can actually see how many of these actually have multiple systems, right? If you look for the orbits of extrasolar planets, most of the detected planets have a mass greater than that of Jupiter mass. That's an observational bias. And planets with smaller masses are harder to detect. So it's basically an observational bias. This does not imply that all extrasolar planets have larger masses, right? Then the hot Jupiters also, which are observed. Earlier we observed much more hot Jupiters, again being an observational bias. They're about, actually this is an older slide, so this is 2017, but now there are more than 4,500. So by 2017, there are about 3,700 confirmed planets, and you have certain amount of them which were the terrestrial types and the giant types. As of January 2020, NASA and Kepler's test missions have identified 4,300. There are two more zeros which are gone there. And you can actually see online a whole set of planets which are discovered by them, right? So I'll wind up with that, and I hope you enjoyed this, and please put up your questions. Thank you.